Okay. So a couple of things before really starting. So just to remember you that I put my material, my teaching material on this page that you can find, as I told before. So you look at my first name, my family name Mona, and the lab Perimag, and then okay, you will find it. Okay, so just to tell you that I reorganized a little bit the material of last week. I decided to have a number of chapters corresponding to the number of topics. So basically, there are in order 1, 2, 3, 4, 5, and so on, so except the one. So the one contains what we could say theoretical material, so very basic principles without any interesting application in mind. In contrast, the other will talk on the main example I take, that is reasoning on the semantics of programming languages, and a little bit also using Coq for proving the correctness of functional programs. So, for instance, this one. So these two last topics are related, because when you provide the semantics of a programming language, you have to define a number of types and functions. So it is basically the same technology. Okay, so in the theoretical, so far, not that theoretical, but okay, we'd say basic theoretical material. I mean, you don't need to read everything in this one, the next one, etc., before the rest. Okay, so it's more interactive. When I need a new notion, I will add a new Coq 01 init theory material. Okay, so up to now we have seen the contents of introduction, theory 1, theory 2, and I will talk today about theory 3. Okay, and I will also talk about what maybe this one, the 3, the 4, and the 5. I think it's the material of today. And okay, I have other material already prepared, but I did not put here, not in order not to confuse you. So remember, I expect that you practice, because if you just hear what I am doing and if you don't practice a little bit after, you will not. It will not very efficient. Okay. So please redo the exercise I showed to you. I will provide a number of solutions, but not all of them, because I have not the time. And moreover, it's more important that you try by yourself. Okay, and then don't ask me questions. You can write directly to me or write to somebody in the room here, and they will maybe just a little bit and transfer the question to me. Okay, so it will better in this way. Okay, that's all for this thing. Another thing I wanted to do is to make a little bit of advertisement for this excellent book. Okay, so I don't know if you can see it on the screen here. Okay. So Professor Deng wrote a book on lambda calculus, Coq, and OCaml. So I could not read the Chinese, but I could read the code, so I can guess the Chinese contents from the code. And there is a lot of interesting material inside. I will cover many things inside it, an equivalent maybe with a different point of view, but there are a number of things that I don't want to cover. For instance, co-inductive types. So Professor Deng talk about this. So it is a good complement on my lectures if you want.
Okay, thanks.
Okay. So let us go back to the main contents now. So here is a very simple file. So I think it's called the Coq 4 apply V. That's the name. Okay, I can show you again here the name. Where it is here. Okay, so I will now talk on this one. Okay, so of course, so number 4. So this one is very short and very simple. It's more kind of a rehearsal of what we have seen. So basically, the tactics apply that we will use quite often, which is a special case of refine that we talked already about refine, and another one which is called revert. Okay, so basically, so tactics refine, intro, apply, and revert. So remember that intro X is the same as refine fun X or something. Okay. So you say that you introduce a hypothesis or a variable in a function. Okay. So revert, this one is new, but you can think it intuitively as a revert of the converse of intro. So if you write intro X and then revert X, you just recover the previous situation. Sometimes it is interesting because you could have intro X, intro Y, but you just want to revert on X. You want to keep Y in the context. Okay, so maybe we will see examples later. So revert, you can explain it again in terms of refine. So revert is refine some whole applied to X. Okay, so you want to find a function which applied to X will satisfy the goal. Okay. And it is yes, it's also followed by something maybe I didn't explain before. Yes, it is explained here. Okay, so you have this tactics which is called clear. So you will see examples soon. So clear just removes this hypothesis or this variable from what you see on top of the bar. Okay, so because when you are doing big proofs, typically, okay, you have too many things that you don't need to use everything, so you want to clean from time to time. So also the keyword is not clean but clear with the R here. Okay. Okay, so okay, and so apply. I think we already saw it. So apply is a kind of dual of revert actually, because in revert it is a refined whole applied to X, and apply is the converse. It's refined F applied to a whole. So you see the duality here. So apply actually is like refine. Okay, this is the special case of refine when you F is a unary function, but F could be a binary, ternary, and so on function. I mean a function which is applied to something and then provide a function. You remember, binary functions are unary functions in functional programming languages. You apply F binary function to one argument, if it is called the partial application, and then you get a unary function. Okay, so anyway, you can read what I already said on this, and so on. Okay, so that's the presentation. So what did I wrote here? Example, if you have this context F, okay, of type T1 to T2, and you want to have a of T2, you want to prove T2 or make some object inside T2, like how to say that. So then you could say, okay, I just apply F to something which is still unknown, and then I will get a T2. So you see that you when you say apply or this kind of refine, in fact, in practice, what you do is that you look at this part and you look for something which with relevant hypothesis, whose conclusion, his last type here, is the same or compatible with the type that which is here. Okay. Typically, when it is exactly the same. Okay. So then you can say, okay, if I apply F to something of type T1, I will get a T2. It's obvious. Okay. Okay. Last thing that we saw, yes, the last, I think, yes, here. So again, so when you want to reason by case on something, on the possible values of some expression E, then so the functional construct is match E with, and you provide here the different possible cases. So okay, here I have 3 constructors with possibly 1, 0, or 2 arguments. So okay, so this is and when you in a refined mode, you just say, okay, I want to perform my pattern matching, and then if I don't know at the moment what is the answer here, there, and there. So if I don't know the answer at the moment, I put a joker, okay, underscore, and the effect is the same with the tactic destruct. Okay, so destruct E as, and you have to say, okay, I have 3 cases, and I provide a name X, so the same as here. No name here because const2 has no contents, and he const3 has 2 arguments, so YZ, the same as here. Okay. So remember, in destruct, you don't name the constructors, while in programming mode here, you have to name the constructors. So here you have more freedom. Here you could use another order for const1, const2, const3. You could sometimes it's convenient because, for instance, you want to say something about const2, and for all the others is the same answer. So you would say const2. You could say something like this, for instance. So you could say, for instance, I want to look for something here, and for all other cases, okay, I have some kind of default value, okay. Okay, so something I have to provide. Just an example. Okay, so you can write this in interactive mode. I mean, in using a programming construct. You cannot do the equivalent with a destruct. Okay, so basically, refine match is richer from this point of view. On the other hand, so here you have to remember the precise name of the constructors. Here you don't have to remember. So I put the names here in comments, okay, but I'm not obliged to do that. I can just say something like this. So, and usually it is what we do. Okay. Okay, I can remove this one and this one. So this is something shorter. Okay. Also, okay, and you can even do something like this. You can forget the names here, and then Coq will invent some names for you. Usually the names are in some way compatible with the definition you had. So quite often the names are not that stupid, but personally I dislike this kind of thing. Why? Because as soon as Coq provides names, it means that in your script you will use these names. So your script will depend on the algorithm used by Coq to create names. Once again, usually these names are quite relevant, so it's quite natural. But if the algorithm change for one reason or for another, or it could be also your problem. I mean, these names depend on the way you named the names you use in your own definitions. Okay, the names you use in the constructors or these kind of things. So you when you run a type, you use names. Coq will reuse these names basically. But if you change your name, your mind, for instance, you want to replace some n by x or something like this, then Coq will probably change his way of naming things in the script, and your script will become will not work any longer. So it's much better to take the time to write the names here. In this way, your script will not depend on anything else. So it's much more robust. Okay, so not recommended. Okay. This one is still okay, it's shorter. The constructors, okay, it's only a comment, and if you change the name of your constructor, okay, in that case, this command will be just with the wrong comment, but it still works. But here, it's more dangerous. Okay. What else? Okay. So another thing I started to talk about is the universes of Koch. So we have seen that we have a universe called set, which contains all types you use for programming. So remember, you have the type of natural numbers, okay, piano natural numbers, so nat. You have also typically our colors, the type you define. And you also have the functions, typically a function from nat to color, for example. This type, the type nat to color, is a type set. Okay, so let us write this. Check, for instance, nat to, okay, color is not defined here. Okay, I will just repeat nat for convenience. So you see that you don't see because it's hidden here. No, okay, don't see because okay, I arrive here, and you see the answer here. Small. Okay, you see that nat to nat is clear. Okay, nat to nat is of type set. Okay, so now if I check the next one, this equality, 2 is equal to 2. So in a programming language, you would say it is something like a Boolean value, but okay, I don't want to talk about Boolean for now. It's anyway, it's something else. It is a prop. It's a proposition. Okay, so a proposition has nothing to do with a Boolean. A proposition is something that you want to prove. You don't want to prove a Boolean. You don't want to prove a nat. You don't want to prove something like this, okay? But you want to prove a prop, not prop, but something which is a prop. So you want to prove that 2 is equal to 2, okay? And I could also check. Sorry. Okay, it's clean. It has nothing to do with the fact that it is actually provable. For instance, 2 is equal to 3. Okay. Okay. You may say it's wrong, but it doesn't matter. It's still well typed. It has a right type, which is prop. Okay. Okay. So something also I didn't want to talk to Orion about that, but you may wonder, well, what is the type of prop, for instance, or set? So in Coq, everything has a type. You have to remember that. Basically, so let us check the type of set. Set. What is it? Type. Oh, so new thing which is called type. Okay. Prop. Also a type. So it is exactly what I told you before. Set and prop are two different universes which are in type. Okay, we may also check type, of course. What's the type of type? Type is wrong answer. It's type. Okay, so you have the illusion that type has a type. So actually, it's an illusion. Okay, because for quite deep reasons. Okay, so if you really say that in combination with the other features of the type system, you get an inconsistent logical system. Which means that if you really have that, you can prove false. So actually, what is written here is not exactly what happened. I think we should try something. I didn't set printing all. How to say that? Maybe like this. Okay. So what? maybe it works. Oh, no. Well, okay, so maybe okay, so I'm sorry. I need to put another command, I don't remember which one, to have to see exactly what happened. But actually, so I don't want to write it formally here. Actually, what you have a sequences of universes. So you have type of 0, which I think that set and prop. No, prop is different, but set is like type of 0, something like this. And then type of 0 is of type of 1, which is of type of 2, which is etc. etc. And actually, it's more complicated than that. It is called the cumulative. The name is cumulative hierarchy of universes. Okay. Something like this. Okay. You have something like this, which means that actually type of say 2 is of type all the other, so type of 2 is of type of 3, type of 4, type of etc. You have a kind of combination. Okay. This is a real thing which is behind the system. Okay, in other proof of systems, you need to use, not to use, you need to write the number where you are, and this is very inconvenient. So Coq has another system which Coq maintains a kind of floating. We should say something like this: floating. Okay. System. So it maintains a number of constraints in order for you not to have a cycle among your types. Okay. Basically, don't forget about this. Except if you want to enter into things like category theory, very theoretical things, then you have to be aware of this kind of things. For everyday life, for a programmer, you just have to know that set is in type, and that's all. Okay, so I mentioned type why? So because I use lists basically, and lists. Okay, lists are lists of anything. You have lists of numbers, you have lists of colors, list of functions. Okay, these basic things. Okay, list of things which are in set. But you could also have list of properties. Why not? Okay, list of equalities. Okay, then and still you want to open them or find their length. So it's the same. So then it makes sense to have a list of things which are either in prop or in set, or maybe list of types. Okay, so if you want to be very general for lists, it's better to have list of things in type. Okay, so that's the basic reason that where you could have a type. Personally, I prefer to use set whenever because what I am using. Okay, since quite a long time, maybe 2004, something like this, when Eve wrote his book. I think it should be like this, or 20 years ago. Before that, people use set very okay in everyday life, and then people started to use type for data types. Yes, I think the basic reason is okay, it's a type. Okay, you name it type, but the real thing behind this is more complicated. So okay, it does not make a big difference in practice. Okay, so you can, or I use set, but if you can write type if you prefer. Usually, it doesn't make a difference. Okay, what could I add on that? Okay, so now let us try very simple exercises on propositional logic, more precisely on minimal propositional logic. So minimal propositional logic is a logic where you have only one connector, which is implication. It's enough for everything. Okay, so I will not have and or because I don't need to use them. They exist in Coq, but okay. No really need. So maybe I will talk about that once. Okay, so let us open a section ABC with the propositions ABC here. Okay, and also I want to have predicates P, Q, R over NAT. I just take NAT because I don't want to reason on numbers. It is just because it is one of the predefined data types of the system. That's the only reason. I don't want to waste my time with colors, so but I could. Okay, so I have these variables, not from so predicates. By the way, what is the type of NAT to prop? What do you think? What should be the answer? I think it's prop. I think it's type. Because I think it's higher than, at least as high as prop. So prop is of type, so I think it should be type. Well, it's not that important, but that's interesting, the way it's displayed. It's displayed in this way. Nice. Usually, Coq tends to write an arrow whenever possible, but not in this case. Yeah. Okay. Okay, but anyway, you see that the answer is actually type. Okay. But okay, just for the fun. Okay, let us now prove the following thing. Okay, so I want to prove that implication is transitive. So if A implies B, and if B implies C, then A implies C. Okay. So what could we do? Oh, sorry, need to be bigger. I know why. This fall. Sorry, it is because I wrote that set printing all. The set printing all. I think it is an effect of this one. Okay. So okay, let us. Anyway, it had no effect, so I will remove it. So here I think that okay, now it's written not to prop. Okay. So now we get again A to B implies B to C implies A to C. Okay. So we see that we have two things to introduce, for instance. Okay. Okay, so I call the first one A to B, A implies B, the second B implies C. Okay. And now I have to prove that A implies C. What do you suggest? So I have to prove an implication once again. I have an arrow. When I have an arrow, what is the tactic to be used? Introduction. Each time I have an arrow, okay, I could use, okay, I could have A implies C here. In that case, there is no need to, okay, I change this just to show you that intros is not mandatory. In that case, it's better to call it AC. Okay. To introduce something, I can just say, oh, I already have the answer here. So here I could say, for instance, exact AC. Okay, finished. No more goals. Okay, but okay, let us go to the real statement. This one, so with BC now. So here I have no simple way to answer. Okay, so here again, this thing does not exist any longer. So let us introduce something for A, a little a. Sorry. This. Okay. And what do I have? So I just have to, it is very simple. I just have to look at the conclusion here. Do I have something on top of my bar which concludes to C? Yes, I have this one. So I could say, okay, I could try to apply this one to something, and I will get a C. Okay, so I can write apply BC, and now I'm left with a new goal, which is please find a B. Okay, so now I have to find a B. Once again, okay, I see something which finished by a B, so I have this one. Okay, okay, so let us apply it. Apply AB. I now I have to find A. Okay, so I could say apply A or exact A. Okay, so it is very okay. Okay, just have to remember the name of the tactic, but nothing. So what is interesting with this exercise is that we can find a functional interpretation for it. So if you read the same statement, not as with propositions, but with types, data types. Okay, so imagine that ABC are of type set. It makes the rest makes no difference. I have a function from A to B, a function from B to C, and I want to provide a function from A to C. Okay, this is just what we call usually sequential composition of functions. Okay, so the little O. Okay, so we can have this reading. So let us restart. I could say refine. Okay, so okay, I could say I could do that at once or step by step. Okay, for instance, if I do that step by step, I would say, okay, I will introduce the first one. So it means that I say that my result is function of AB to something. This is my first intro, okay? And it is only one introduction. If I want to do two introductions at once, I could say find AB and BC. Do that, okay? And then I could say refine fun of A, return something. So the same, I follow exactly the same scheme as before. I am here after the intro A, okay. And now I could say directly the result. I could say exact or refine. Refine. So I apply something to B. Sorry, it is BC applied to something. Okay, BC applied to what? To apply to AB applied to BA. Okay. So usually you think with functions with name of function like f, j, something like this. So maybe you can rewrite this another way. So we'll restart. Okay. So we could say start refine. So let us call this the first function j of f. Okay, let us call this one f. This one j. Okay. The next one with the x. Okay, this is more usual if you want. And then you would say this is j of f of a of x. Okay. Or if you want to write it okay, in one step, you just say refine or exact in that case, there is no hole. Okay, so like this. So I just copy paste what I wrote. I could put the X for on the left of the first arrow, it's equivalent, and then G of f of X. Okay. Okay, this is exactly the usual function composition that you learn at primary school, at school. Okay. Okay, so I'm finished for this one. So I should put QED actually. So the next one is correspond to a common combinator in lambda calculus. So it's I think this is called the S combinator. If you know about combinator presentation of lambda calculus. So it's okay. So its type is A to B to C. So it's similar to this one. Or somewhat similar. I mean, the conclusion is the same, A to C, but you have different premises. You have a binary function here, A to B to C, and A to B, and you want to prove the last one. Okay. So at first you have to think a little bit, but if you just follow the types, it's not that difficult. So let us try. Okay, so let us introduce a first function. I call it J, another one which is called F, and some X. Okay. So I have the three things. So here I chose to write the X with the functions, to introduce it at the same time. Okay, anyway, now I have only one solution. I need to apply J to something to get a C. I have to apply J to two things, J to an A and then to a B. Okay. Actually, I have already an A. Okay. So what I could do, for instance, here I could say, okay, refine J, apply to my A, or it is called X, and then it's too complicated. I will look later. Okay, and something. Okay, so J of X should be and something should be a good answer. So what is the type of the whole here? What is the type of this one? So it is B. Okay, so I will have to find a B. Okay. And now how could I find a B? Okay, I could say apply F, and then I will have to, okay. So I could say again, refine, so in that case, just F of X. Okay, so, and then okay, I'm finished. Or if you prefer apply style, you can say apply F. Okay, so I apply F, which is correct. Let's try something else. Apply G, just to show you that apply G does not work. Okay. So it is interesting to see what Coq returns to you. So Coq says, okay, in this environment, so it just repeats what it has. But in that case, it is exactly the same. But in complicated situations, so where you would have some complicated function with some code, then you could have messages like this, but with more context, with things which depend on the way the function has been defined. Okay, so you see exactly all what you have in your pocket, and then, okay, the answer is C is not the same as B. Okay, there is no way to say that they are the same. So unify them. Okay, this is the terminology. So it means that actually you want a B and you provide a C, that's not the same. Okay, so J doesn't work. G maybe. Okay, let us try F, of course. Okay, and F finished by, okay, so B and B match. Okay, and now I have to find A. Okay, so just X. This. Okay. Oh, by the way, I can show what I had. I could do that on the proof. This command is very useful sometimes to see what you are doing. Okay, show proof, and you. Okay. So you see exactly the definition of the S combinator. Lambda G, lambda F, lambda X, G of X of F of X. Okay. And now you can see that first order logic is just as simple as propositional logic, because the for all is managed in the same way as an implication with, I mean, just with introductions. So here we have something similar to previous one. So if for all n, P of n implies Q of n, and so on, Q, R, and P, R. So you can, you see a kind of transitivity, but each time I have a for n. So I cannot use the previous theorem here, because this thing, for instance, is not a special case of A implies B. This is something which is more complex. It is a function. This the functional interpretation of this one, for instance, and the other one, it is a binary function. It is a function with two arguments, an argument of type NAT, and an argument which is a proof of P of n. So two arguments. Remember this thing. So I have function of two arguments, function of two arguments, returns a function of two arguments. So similar, but we need to redo the proof. So let us introduce, or refine if you like. Okay. Let us use intros. So intros, let us say PQ, QR. Okay, what do I get? I get this one. Okay, so now I could say intros of n. Okay, the n is better. I could say x if I want, but okay, let us reuse the same name, and then a proof of Pn. Okay, okay, I could p, a little p. Okay, I have all this, and now, okay, no, I will use another name, because I want to show something. Let us say x. Okay. Okay, that's better, because now what I have here is not written the same as the conclusion here. So this is what I want to say. Okay, so if I write n is correct, but less a little bit confusing. Okay, so no, here I have something is clearer, more clear. So I want to prove R of X. So I have to something which is R of X, or which could be of R of X. So the only one I have here is here, R as the conclusion, but of n. But no problem, because this n is not specific. It is any n. So you see that if I specialize QR to X, so if I apply, so let us check. The good command in this situation is check. So let us check what is QR applied to X. Okay. I will try to apply to n. What should be the answer if I apply to n? No. If you try this, you get an error, because n is not defined. So you are not in first order logic. So nothing to do with logic. The only thing is that the only thing I have in my pocket are ABC. By the way, ABC are not useful. I can do that. Clear. I wanted, okay, A, B, C. So I don't need them. So sorry, with lowercase. Okay. Okay. So the only thing I have, okay. Let us try also clear P, Q, R, or just P. Here, Coq will complain, because P is used in hypothesis PQ. So this one, okay. So this hypothesis use P. I cannot remove P for my environment. It doesn't make sense to have something which talks about P if P is not known in advance. Okay, so clear P. Okay, so fails. Okay. Now check QR of n are the same. It's dual. I mean, I want to talk about something which is not introduced. It's not unknown. So again, was not found in the environment, I think, in the current environment. Okay. So n does not exist. Okay. So, okay, this one fails. But now let us check something which is allowed, that is QR applied to X. So this time I will get, okay. Could you guess what I should guess, what I should get now? So QR, this thing applied to X exists, and moreover, X has a right type. Okay, it is a NAT. Okay, so the rest will be QX, rho, RX, right? Okay. Okay. Interesting, because I see that my conclusion is Rx here. So using this one makes sense. Okay. So I can apply this one, and Coq will leave you with something to do, which is please give me a proof of Q of X. Okay. So sorry. So apply QR of X. Okay. Okay. Now we need to provide a proof of Q of X. So now same thing. I have this one, which can be the conclusion of this one, it can be unified with this is here that the word unify makes sense. Okay. So again, I can do something similar. PQ applied to X, so no surprise. Okay, this is perfectly explicit. But now let us, okay, so it works, okay. But let us try something else. Just PQ. So more advanced use of apply. Because this time PQ, it is not clear that PQ could work. Actually, it works because PQ applied to something. So if you make the good guess for n, it can succeed. And in fact, the algorithm followed by the proof assistant to find the right n in this situation. So you don't provide the n, but you ask Coq, please, could you guess the right n for this to apply correctly? And this algorithm is called unification. Okay, so this is something which is quite quite common in how to say, proof automation. Okay, many languages are based on unification. It is also used for combining for finding types, for instance. Okay, it is typically something which is related to type inference. Actually, this is an inference of type inference here. Type inference means that the system tries to find the type of something, of a function, or an expression, the type of an expression. So you didn't write the types everywhere, but there is no choice. There is no choice for some reason. Okay, so Coq use this type of inference in many situations, and actually it was one of the main things introduced by the ML family of languages at the beginning. Okay, so I don't want to enter into all the details of type inference. It's just something like okay, guess the type, the right type, and Coq is able to do that, and you are left with exactly the same thing. So actually, if you look at what happens, so here you can see the proof. You see that here you can see that. So introduction of okay, PQ, QR, we cannot see them. Yes. So X, and what is interesting is here you see that I have QR applied to X. It is exactly what we write here, and then the result, the thing which is here, I mean QR applied to X. So the whole here, which is obtained by applied PQ. So this is PQ applied to A, and we see that Coq guessed. Okay, and still we have a hole here, which is called question mark goal, which is this one. Okay, we have a goal. The goal is here. Find a PX. Okay, not difficult. Okay, you can say exact P. Yeah. Okay, so once again, it's important to be aware of the functional interpretation of application. When you use, for instance, okay, when you use, you'd say in ordinary language, a hypothesis specialized to some value. The value could be X, it could be P of X, or no, QR of X, I think, something. Okay, so it is just functional application, and in the other direction, an implication or a for statement, okay, are just functions, okay, making functions from arguments and providing a body. Okay, so here I provided given these two functions, I was able to make a new binary function depending on n or x if you want, and a proof of P of n. Okay, so that's all for this one. So maybe I will add the material on types on the website, but I will not add the solutions. So please don't. I really want you to redo the exercise by yourself. It is the way for you to really remember what I said, and also to become familiar with all these notions. Okay, so now let us go to the next part of the lecture. Okay, so I'll go to my planning. Okay, I will go to a little bit of theory. Yes, okay, so this one is easier than what we have seen last week. Okay, maybe I should do something like this. Okay. Okay, so I will talk a little bit about the official definition of lists. Okay, we have already seen list of colors, or maybe list of data. I don't remember exactly. Anyway, as you could expect, lists are something. I mean, most interesting functions on lists, or we call them sometimes generic functions on lists, don't depend on the elements. Okay, for instance, if you compute the length of the links of a list, you don't care about if it is a list of don't know, colors, whatever characters. If you are in okay, so the right way to define list is like this. You say, as before, inductive list. So I like sets, so I will say it is I will say at the moment it is a set, okay? And I have a new thing here, which is a parameter. So I say there are a list of elements of type A, okay? So the point is that list alone is not a type. I have to say, for instance, list of nut or list of whatever, okay? List of something is a type. So here it's important because here for the cons constructor, okay. So okay, this one takes an element in A, but then it takes a list of A and it returns a list of A, not a list alone, okay. So you have to you can see list as a kind of function, a function which takes set and returns sets, or types and return types, okay? But it is not a function which analyzes its argument. It just uses its argument and put it here and there, okay? It just uses its argument and, okay, that's all, okay? But okay, but it works like a function. I mean, it is a function applied to a type. Okay, this is what I said here. Maybe the functional notation means list can be seen as a function, taking the type, okay, and returning the corresponding type of list. Okay, and no compute. We have already seen things function like wow last week. So these functions are more complicated because they take a data type, for instance, a color, and according to the color, they return a data type. So this one takes not a data type, it takes a type. Oh, no, sorry, it doesn't take an element, a specific color, but it takes a type, but we cannot analyze the type. But similarly to wow, we return a type. Okay. So A is just transferred as is. Yeah, well, maybe I should. No. I have again to make this one bigger. So what did I? Okay, so now, what is the point of the next example? So I want to write using this type, so this more general type, I want to recover a list of nuts. So basically, I should write all this. So a little bit annoying, but at the moment, just accept it, okay? So I define the list made of the three numbers 6, 2, and 4. So it is a list of nuts, okay? And then I get it using the constructor cons, and I have to say, okay, something which is unclear here. I should. It is that cons takes an element and then a list, but that's wrong. Actually, cons first takes a set as an argument. Maybe if I check, I should write this. Check cons. It will be more check cons. And you see that the full type of cons is this one. Cons take first the type of the element, then an element in this type, A, and then a list and so on, okay? So the full type of cons actually contains this four before all the rest, okay? So what you see here is a little bit misleading. If you forget to check using this command, you can recover the full type, at reading, by remembering that actually all the parameters here before this colon are also parameters of the constructors, okay? So A is also a parameter of nil, okay? So I show for cons, this is the same for nil. So here I should say not cons of 6, but cons of NAT and then 6. It's normal because if I just say cons of 6, how could I say is okay? It doesn't make sense alone because 6. Okay, I have to say to explain what will be this type. This 6 it is in NAT. Okay, so cons first applied to NAT, and then okay, I am allowed to talk about a 6. And again, the sequence is the same. Cons applied to 2, cons applied to 4, but always with a NAT. And at the end, nil applied to NAT. Okay. So this is the full list. Okay. So a little bit complicated. Now we have another mechanism which says, which allows us to write less things. So you see that actually, when I write cons NAT 6, as soon as I write the 6 here, there is no choice. We know that this argument should be a NAT. So Coq is able to guess this the content which is at its place, and we just write this cons applied to. Okay, please guess what it is. Okay, so it's easier to read. I mean, okay, so just a small hole and then 6, and similar here. Okay, find. Okay, 2, and okay, a guess 4, and a guess. Okay, so it works. Okay, so you see that it works here. But now if I print it. Okay, Coq will print in the heavy way because okay, this is the whole thing. So when you write this, actually, it is exactly the same effect as before, but just easier to type, easier to write. But the real content is this one. Now let us go a more convenient thing, which is to state that A is an implicit argument of my list. So how to do that? So I say that, so the command is called arguments, okay? So again, if I check nil, Coq will say, okay, nil has an argument which is called A. Now I say that the argument of nil is inside braces, curly braces. So when I write curly braces, it will mean, okay, next time I will not consider even, okay, I don't even have to write this. And okay, so things will become easier to read. And same for cons, I say that the first argument is implicit in this way, okay, and then I can write exactly as you would like to type it, to write it this way. And if you print it, it is again as before. Artifact. So again, it is just a presentation, okay? If you can still have, you can see everything. So you put set printing all, and if you print it, okay. Actually, I see many more things because even 6, for instance, becomes S of 0, okay, etc. The point is that for what I wanted to say is that, oops, sorry, is that you have. Oh, okay, I lost it. The point is that, okay, sorry, I need to recover. No, here, streamers. Okay. Okay, so the point is that you see the NAT here and the NAT there and so on. Okay, so this sign here, arrobas, this at sign, okay, means that okay, this is the explicit version of cons. Okay, so okay. Okay, I could check. I could say, for instance, okay. Okay, let us about this printing angle, which is too complicated. Okay, so I recover this one. I can do something else. I can do, I can just, for instance, show you this argument. Now I put usual parentheses, okay, like this. Ah, okay. This is okay. So Coq complains a little bit, but we have the answer of what you have to do. This command is just asserting the names of argument. Warning: if you want to clear implicit arguments, which is what I want to say, add clear, you know what? Ah, okay. Let us say what is is printed. If you want to clear notation scopes, and so scopes, I don't want to talk about. Okay, the command is here. Add clear implicit. So what I want to do actually is this one. Argument cons clear implicit. Something like this. Maybe like this. Ah, yes. Okay. So this time, if I print list okay, I will get surprising. I would like to expect to see the NAT here. Cons of okay. It didn't complain. Maybe okay. Sorry. Okay, I don't want to waste too much my time here. Maybe okay, I will try at home and show you the right command tomorrow because okay, this is something a bit not that important actually. Okay, the basic thing is that it's more or less usually. Okay, I am a bit lost here because we never need to do that actually. The important point is that usually you want to put some arguments to say that they are implicit like this, and then you are happy. And if you need to consider, for instance, a non-implicit version of cons, the thing that you can do is the following one. So okay, so I will remove this. You can, for instance, define okay, definition or example, okay. Okay, list 2 to 3. I could say like before, cons of so 2. Okay, and if I want to be more explicit on the second one, I could say arrobas cons nat 3. I think this one should work. Cons avec with the O. Okay. If I try another thing, for instance, nat to nat. Okay. So okay. So here Coq complain because 3 has type nat while it is expected to have type nat to nat. Okay. So okay. So just to say because sometimes this thing is very useful in some situations because okay, implicit usually are very convenient, but sometimes you need to have a fine control of what you want to write. So it's useful to know this arrobas. Okay. Okay, so that's all. Now, if you want to write a function like length, okay, length here has okay, so this is the ordinary function. So here you say a between with parentheses, okay. So this is the basic definition, and then u of type of a, and then the usual definition. So here you see that there is no a because I have this convenient command here. Okay, but still, when I make my recursive call, so the explicit with explicit type argument. So when I call it, I have to repeat A, okay, because length expects an A and then a list. Okay, so it works. Now you can compute, and when I compute it, the point is that I need to say length applied to NAT and then applied to some list. Okay. Of course, I could be more lazy and say, okay, apply my function length, and anyway, as I put here a list of NATs, okay, you will be able to find by yourself what is here, and so you get the 3 as expected and no complaint. Now, okay, so that's the point for illustrating this usage of curly braces here. Okay, now I have the same definition, so I give another name in order to keep the 2 definitions. So the usual length, so I say that A now is an implicit argument of my function, and in the recursive call, I don't have to, I need not to give the A. If I try to put the A, Coq will complain. If I try this, okay, Coq will say, blah, 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 error in this environment, the term A has type set, while it is expected to have type, don't know, maybe A or something like this. It has, okay, have type, okay, something complicated. Well, anyway, okay, so sometimes the message of Coq are a little bit cryptic, but anyway, see that it means that, okay, that this A is here. So let us arguments. Some of them are implicit, some of them are explicit, and in general, it's obvious for you to choose the right, to make the right choice. Okay. Okay, so maybe. Okay, so she's okay. I prepared something with clear implicits. Okay, this is maybe. Okay, I think what I forgot before was this column here. Okay, okay. Maybe I should probably read more carefully the message of Coq to see that, because I'm not able to remember this kind of thing. So okay, I just read the output of Coq and copy it. Okay, so this one is okay. And now what happens now? Oh, yes, fail fixed point. So why does it fail? Yes, I wanted to show. So the point I wanted to show is the following. Okay. Another, okay, all these small experiments are because the error message of Coq have to be understood. So let us copy it here. See it completely. Okay. The point is, so this is a little bit subtle. So you see, so here, okay, I use the usual, the basic definition of nil with no trick about implicit arguments. So everything is explicit. So I should be able to write something like this. So I say that nil should be applied to A, and const should be applied to A. So everything seems correct, like here. But you have this message. And what basically Coq says is that parameters do not bind in patterns. So how to understand that? The pattern, it is this or that. This is a pattern. And remember, in a pattern, you have 2 kinds of things. You have constructors like list, like nil or const. If you have binary trees, you could have n or leaf or whatever. Okay. If you have if you have natural numbers, you have s or o. Okay, so your constructors. And the second kind of thing you have are variables. Okay, and you remember that when you have variables, these names are bound to the to the actual things for, oh, sorry, the actual thing is here. So here you get a L from the function call. So L will be some specific list, like list 6, like this one, for instance. Okay, so you get a specific list made of constructors. Okay, so made so the list you have actually is, so for instance, counts of NAT 6 and so on. Okay, the list you get actually is like this, but the point is that actually the A, you cannot okay, bind A to anything. Why? This is because A is given here, and as A is a parameter of this type, list A, that it is a parameter, it is not caught by pattern matching. Okay, so maybe I should show the, okay, okay, maybe you will understand better if I show another definition of list. So I will copy paste this one and show you another possible definition, which is actually different. So I will write it here. So I will give another name, W like wrong list. Okay. And this one, it will be similar, but A will not be a parameter like this. It will be put here. And I will say that nil has type for all A, list of A. Is very similar at first sight, because here we see clearly the type of const. It was exactly the type we had before. You remember? Const. The full type of const was exactly this one. So if I write things in this way, then A will be bound. So what happens? Okay, so it works. What doesn't work? Why? Let me see the message. Ah, okay, I forgot to change. Okay, it is. I should put a W everywhere. Sorry. And again, okay, and now I will have another mistake. Nil and cons are already defined. So here, okay, if I, okay, so I see, okay. I explained before, which is that setting the type, but here we have something which is, okay, if I write this, I get something which is higher in the type hierarchy. So actually, I think I should write type here in order for this to work, because I have a, okay. Well, okay, and if I put a type here, il succeed. Yes. Oof. Okay. Okay. So So now you understand why people prefer type to set. This is for this kind of reasons. But actually, I'm not sure it's a good idea, because this type is not as sympathetic as the previous one. Each level of my list, I in a kind of new type. So I mean, with this kind of construct, this one is actually more or less equivalent, because I have always the same A everywhere. So the same is passed here. So related to what I have seen before, but I could using this thing, I could do something. I could have a list made of from time to time an integer, then something else, etc. I could do something, so I will try. So this one is not very interesting, but this also, how to say that? Okay. Heterogeneous list. So just H, okay? So this one actually will be a little bit simpler. I only have a type here, and I will say, okay, I remember this one. I remove this one. I remove this one. Let us put a H here. Okay. I think it works. What do I say? Okay, I have to, what is A? Okay, cannot infer the type of A. Okay, it could be set or it could be type. Let us try to be simple with a set. I think I will, okay, it works again. Okay, then he is able to infer that A is a set as well. Okay, so here I can make something like this definition. Example, okay, H list, okay, okay. I'm trying to find him. So I could write something like this, const H of, say, not, and then 3, applied to const H, for instance, not to not, and then fun x to x plus x times 2. Well, let us stop and nil H. I think it should work. No, as type set. Okay. Actually, this one is stupid. This one I don't need to. Okay, because I don't use A. Okay, so let us remove this one. It is okay. No use. But now I have to put this one. Put a set here. Okay. Okay, this one is better. Now it to one. Okay. So you see that it is a list made of a number and then a function, and you could have anything. Okay, so you can have these kind of things. So you see that here the power of the type system that we have, the power of the inductive. So usually you have okay, you have a list made of anything, but at each cons you have to declare what is the type of what you have, and this type could change. Okay, so then it makes sense at pattern matching to say, okay, now, okay, so you could say something like this. Example, okay, function on a function of f, which takes a list of type list H. That's all. Match L with, okay. By the way, you could see here that I use a little bit an abbreviation. Usually I write fun of A, L, etc. But for fixed point I cannot. Okay, I need to write this way. Okay. Okay, so this is okay. Now the possible syntax without fun directly like this. Okay, match L with. So let us say nil H. Oh, I will return the length. Okay, so I will return 0, for instance. And here, and if I have a const H of, this time I have my two arguments. I have A, okay, and then I have some element, well, and the rest, okay. Okay, I didn't write the fixed point, so I will stop. Okay, so just 5, and that's all. Sorry, and if I put a fixed point, I can. It's not. It's okay. It is not the length. It's some number. I think this one list. Sorry, it is H like here. Okay. So here it makes sense to catch this argument here. Okay, because this argument is really a part of the content, it's a part of the contents of this constructor. It is a possible new set. Okay. Now, when I wanted to illustrate my mistake before, where did I get? Okay, here. Yes, here. Sorry. Here, A is not really. It's not a parameter of A. A parameter of const. It's okay. It is there, but actually, I cannot choose. Here, I get a new A here in the last example. Sorry, it was here. Yeah. Okay. Here, I actually I could return something. I could return it. I could return, for instance, a set. Okay. Here I could return A. Okay. Oh, okay. Because I said 0, it was wrong. So, okay. So, okay. Okay. Let us say, for instance, not. Okay. Okay. So, okay, this is a list, quite strange list, but okay, it makes sense. I can return A because N is discovered when I perform my pattern matching. Okay, but here is very different. A is not discovered. A is constrained to be this A. Okay, so I cannot write this. So here the parameter blah blah blah. The command is init failed. Okay, so and it says parameter do not bind. Okay, they must be replaced by underscore. So you have anyway the message is good here. You know what you have to do. You have just to write this. So okay, I have something, but okay, I don't have to provide a name for it. I know it. It is A. Okay. Okay, so somewhat technical things on these implicit parameters. So two things. We discovered the implicit parameters, which are very convenient, and the other things is this notion of parameter of a type, which is handled in a specific way in this kind of situations. And you need to write this underscore at this place. Okay. Okay, so now what else? What else? Okay. Okay. Okay, it already exists. Okay, this is okay. Actually, I wrote and I added some material meanwhile. Okay. So. Okay, so I will clean it later. At the moment, I just put a fail because it is the function I just wrote it earlier. What did I say here? Oh, yes. So, okay. Just to show that if you write this way, so you get the message we have seen before. And if you try to heal it with an implicit argument, it's not the point. It's just you get the same the same issue. Okay, so okay, don't want to. Okay, so this is again. Okay, here I chose another name, so it works. So with implicit arguments. Okay, so if you want to write the length function, so okay, this is the right way to write it. If you have removed the implicit argument of nil and const. Usually you don't remove them, so you don't see this kind of stuff. Okay. So what we get is essentially the definition given in the standard library of Coq. So up to 2 minor details. So let us see them. Print list. So the first thing is that, okay, so this is my list. Okay, this is my list I defined earlier. So let us reset this. Okay, so I forgot everything defined from a list. And then if I require the list of the standard library here, and I print it, what I get is more or less the same thing with a minor difference, which is that we have a type and return the type. Okay. Another difference is that the name of the constructors are made of lowercase letters. So small n here and small c here. Okay, so this is because coq is okay, accept it. I used uppercase letter because OCaml, in the OCaml language, the constructors need to start with the uppercase letter. Okay, so in my course in France, I teach coq and OCaml at the same time, and in order not to get confused, I take the same convention. But actually, coq is more accept more things than OCaml in this situation. Okay, so this is a detail you need to know. Actually, if you write at the same time coq code and OCaml code, so something which looks correct in OCaml suddenly it doesn't work just because of this stupid convention on stupid. It's a little bit different. So there are good reasons for different convention because the objectives are different, not the same language. Okay. So that is what I said, lowercase letters. Type instead of set. Okay. I think that's the end of the file, basically. What time is it? Okay, so we will make a short pause. I'll just have a look on the conclusions here. So, so we can have list of enumerated types, list of numbers, etc. We can have you have user-defined data types. So list of user-defined data types. Okay, no, sorry. I'm talking about these types. This actually this stack of types. Okay, so which contains actually all kinds of things you usually use. Okay, tuples and so on, lists, etc. So basically, all these things usually are in set. Okay, but sometimes you need to talk a little bit about higher types. So, okay, so if you do categorization theory, usually called the theory of abstract nonsense, okay, then you need types. Predicative, this is what I explained earlier. Curly braces, okay, so this is important. Okay, and just to finish, okay. Another convenient thing is that instead of writing const and nil, you could use an infix notation. Warning is a little bit a little pitfall here. So if I define this one, this list, I can write this way. But beware, it is this infix operator is not symmetric. When you write a plus, usually you see, okay, plus is not commutative, but it is symmetric. On the left of a plus, you have a number. On the right, you have a number. It's here different. On the left of this thing, you have an element, and on the right, don't have an element. On the right, you have a list. This thing is actually, if you write it completely, you should write like this, and then like this. This is a real thing, okay? Okay, so okay, so a definition. Okay, I want so this is a short definition. So the same thing. Okay, they are the same. If I print the first one, okay, you even see something different. You see which is something which is a little bit confusing. You see a bracket like this, a bracket like that, and semicolons here in the middle. But actually, this thing is not a constructor. The constructor is this one, or it is another name for const, if you want, and this constructor, which is another name for nil. Okay? And this thing, it just makes things a bit shorter. And this notation can only be used for a list of a given length. For instance, a list of a length 3. I mean, a list which finishes by a nil. Okay. If I want to talk about a list which starts with 6, 2, 4, and then some variable. Okay. So if, for instance, if I say variable, okay, but it's better with a section. But okay, as you need a pause, I don't want to print too many things. Variable L of type list nat. So Coq will say something. Okay, I don't care. And then if I write the same here, so list second, say, and here I type a L. Okay, so it is a list which starts with 6, 2, 4, and then some unknown list. Okay, okay. So if I print it now, this one, no way for Coq to use these square brackets. I get exactly the same. Okay. Here I have only one constructor used 3 times, and that's all. So if I have this constructor, usually we see things in a shorter way. Okay, it comes from some tradition. Okay, so this is written here. And I just say, if you don't understand okay, what I said before, just use this and don't care about this semicolon. And if, okay, you could also avoid all this stuff by not importing these list notations and define yourself only this notation and that notation, and don't use this semicolon notation. Okay. Okay, so that's all. We can have some rest for 5 minutes.
So ask your list notations.
Hmm?
You show the list notation.
Yes, I think something like this. Maybe notation. I never remember a notation. I think maybe we can write infix. I'm not sure. Notation is complicated because we can have notations with keywords, several keywords, and something like this. I think we can say something like infix. Okay, I will find it. I think I have it in my examples somewhere. Mm. Okay, maybe grep notation. Maybe I will find here. Ah, this one. Okay, notation. Okay, like this. Okay, so we can write this notation. Okay, and the other one. So cons. The point is to, yes. Okay, you see. Okay, so you introduce some variables. This is okay. But if you want to introduce the notation for semicolon, it's more complicated.
Yeah.
But that it is complicated because if you don't want it, okay. Okay. So okay, so that's not that difficult. Just write this. So here, I think this one should work. Ah, okay. Like this. Okay, it works. Okay. This one doesn't use this strange semicolon. Hmm. Okay, so my file is correct.
今天少了，第一天也75，30分钟那现在最后，
感谢学员比较少。
对。
Can we go on?
Yeah.
Okay. So, so now we are in file number 3 on list and natural numbers. So here the lists are basic one list of colors. So, but we could do the same, of course, on parametric lists, as I shown at the beginning of the lecture. So last time, I think we went up to this point. We introduced list, and then so the basic theorems on the append function. So that is nil is neutral on the left, but it is for free just by reflexivity, because the definition is on the first argument, pattern matching on the first argument. This is an important point. App is defined by looking at U, okay, and not at V. So if nil is not, nil is none on the left, it's finished. If nil is none on the right, and if L is unknown, then I have to look all the full list L. So it's an induction on L, okay? And then we moved to associativity, you remember? So the statement of associativity is as usual in math. So append this way is equal to append is the other way. You remember that if you compute, it is not the same complexity. So this one is more efficient than that one, okay? But they return the same result on closed lists. Okay, so did you, I think we didn't write the proof for the solution. So I told you that actually it's enough to perform an induction on just the first of the first list, the others, okay, we don't need, don't care. So I expect that you are able to do the proof by yourself. Okay, so basically I expect that you do the exercise, these kind of things, and if you meet something, okay, some error, or if you can succeed, so don't hesitate to write to me. Okay, so I will start from this place. So basically there is no difficulty here. Now the reverse function. So basically it's written this way. So the reverse of nil is nil, and the reverse of x u followed by u prime is the reverse of u prime followed by the list made of one element. So at the end, okay? And now if you want to prove that reverse of reverse is equal, so I mean, the important theorem is this one, the one I want to have. So this one was very easy for binary trees, remember, but for lists, it is more complicated because lists are asymmetric, and we need this lemma first, which says that appending two lists and reversing the result provides the same, returns the same as reversing the second list, then the first list, and appending them. Okay? So we could try to prove that. What would be your choice intuitively here? So first, let us introduce U and V. Okay. What could I see? I have an append. So okay. So what would make sense is to make an induction on U in order to to see what happens here. And okay, so I will have information here, but not there. Okay, we will see. Maybe I will need to make also something on V. We will see later. Okay, so let us try induction on U. So I have two cases. U is empty, so nil is nil. Or so I think it is okay. This is my I use this constructor here. Okay. So the second one, anyway, I have a U prime, say, and sorry, first an element X, then a list U prime, and an induction hypothesis on U prime. Okay. Probably I could say in all cases I will reduce CBN. So when I remember, if I put semicolon CBN, it means that CBN will be performed on all subgoals. I will have two subgoals. So this, okay, so okay, we will see. If it is too optimistic, I will go back to this point. Okay, so first subgoal, rev is equal to append of rev V and nil C. Okay, how do you think I could deal with this goal? So intuitively, you have an append of this list. For this one is simple, okay? And I have the same list here, appended to nil C on the right. So here you should recognize that you have already a lemma. Okay, so here you want to use a lemma which has been proved before. Typically, okay, because you see, okay, this is basically any list which is repeated 2 times here and there. Okay, so okay, it does not depend on the fact it is the reverse. It only depends on the fact that it is some list. Okay, so I have some list. Okay, so it is a typical situation. I could start. Okay, I was nice with you because I started with a number of basic results. This one, that one. Okay, okay, and now we go to more interesting. But usually, in real life, you have your definitions, and then you want to state your big theorem. Okay, for instance, the Fermat theorem, whatever. And maybe you need a lemma before the lemma theorem. Okay, but I mean, in real life, you cannot prove something, even something as simple like this. You see, this statement is very basic after all. Even such a basic statement may need an auxiliary lemma before. Okay, this is very. It is a common basic mathematical situation. Okay. Here you get something which actually more general, so here, what you have to see is that maybe after all, the fact that it is the reverse of V does not matter. It is just a list which is here and there. Okay. So if you didn't have the lemma before, it's time to think a little bit and say, okay, maybe I stop my proof and I go back to, I go back here and I state a lemma. Okay, so in that case, actually, I already have the lemma. The lemma is here. Okay, I have a lemma. So I remember that its name is this one, Nils C on the right, and it is written in this way. The big one is equal to the small one. Okay, I'm afraid it is not the better one, but anyway. So let us go back here. Okay, so I see that this one could be rewritten to this thing using the previous theorem. So we use, you remember, rewrite. When we have an equality which is especially, I want to take a part of a part of my conclusion. So the part is here, and I want to rewrite it into something simpler, or that's something else, not necessarily simpler. So I rewrite my theorem, which is called like this. Okay, like this. So this is right. Usually, it will work. Now, if I want to be more basic, I could say check this one. Okay, just to see what it is. And then you see nothing because it is small letters. Okay, like this, I see that. And I see that it is a quantified, universally quantified theorem. So actually, I should apply it to rough V. So I should actually say, okay, applied to the reverse of L, V, sorry. Okay. Now I have the real thing I want to rewrite. So I should actually write app cc blah blah app apply to review. This is the real thing. This is okay. The basic what actually happens. This is okay. This one we can understand. Okay. Sorry. Only one dot. Okay, but it's okay. Okay. Okay, and then okay, again this one. No. Okay, so what I typed was rewrite. Rewrite. This W. No, I forgot the CBN. Okay, here, like this. So semicolon CBN in all cases. Okay. Like this. Okay. Once again. Okay. Okay. So what I said that now I can rewrite my theorem either completely explicitly or in a lazy way. So can you? So the name is app Nils. So rewrite app line underscore like this. Nils. Write something like this. Okay, let us try. Yes, okay, and reflexivity. Okay. Okay. Next goal. Okay. This one looks more complicated, but maybe not that complicated. Let us see. We have an append of this one and cons x nil c, and here we have an append rev v, etc. So let us also, in this situation, we have to think a little bit. We have two up here. We have two up, and here also we have two up, one here. Okay, but okay, here we see an opportunity because we have rev of u prime followed by v. So this is exactly what we have here, okay? Okay, so here we have an opportunity to use the induction hypothesis, and then we will have something, okay, we have actually an app of rev v and rev u prime at the, okay, so we will have something which is similar to this one, okay? So let us use the induction hypothesis by rewriting, because it is an equality, which is different, okay, rewrite, I called it induction hypothesis U prime. It is my name. Okay. Okay, please. Okay. So, yes, now we have something which is similar. We have an append of rev v, rev u prime, and x nil c, and the same, rev v, rev u prime, cosine c, but the parentheses are put in a different way, okay? We have, here we first append the two revs and then the x. Here we first append u prime with x, and all this is appended to rev. So it is associativity. Okay. So once again, by chance, I already proved associativity. Okay. So maybe it is just the associativity stated, or maybe not. I don't remember. Let me see here. Associativity is stated up. Okay, up you. Okay, not it's not the same way. So anyway, I can just say rewrite. Maybe it's better like this. Rewrite. So of APASOC. Okay, it is just on top of the screen. APASOC. So if I want to be explicit, I could, but it is a little bit boring. Because I should say actually APASOC applied to rev v, rev u prime, and cons. Okay, so this is the full. If I want to be very explicit, I need to say to put three arguments written here. Okay, which are respectively rev v, rev u prime, and cons. This is what we see here. Okay. But it is a little bit boring to write, especially when you are not very familiar with the keyboard. So let us just try this way. Okay. And we see that now we have exactly the same goals here. And this finished. Okay, so just let's say reflexivity. Reflexivity. Okay. Okay. So you see that basically it is a theorem which is quite short to prove, but here you have some mathematical work to do. I mean, you need to recognize some simple lemmas that you proved before, and if you happen not to prove these basic lemmas before, you need to things a little bit abstractly. I mean, imagine, okay, I want to go again to this place here. So I should do that. Yes, here. Okay. When you see that, okay, you have to understand what happens. You have basically the same things, but put in, okay, in the same order, left to right, but not organized in the same way. So this is typically an associativity relation. So you could say, okay, so here you could think, maybe this equality here does not depend on the real, on the fact that it is a rev, and something like this. It is just some list, some other list, and some third list here, which are again here, there, and there, but with up organized in another way. So it is a general statement on three lists, and more generally, in that case, it is associativity. Okay? So a small mathematical situation. Okay. So I need to remove the QED here, maybe. Okay, so I can progress. Now the main theorem, which is the rev of rev is equal to u. So again, it will be, maybe I don't want to do that. You can do by yourself. It is a simple induction on u, and again, you will recognize that you have to use the previous theorem at some point. Okay, so if I started from the very beginning, because okay, from the very beginning, I just defined up, then rev. Let me show you. How can, yes, using this thing. So I define up. Where is rev? List up. Okay, sorry, rev is here. Okay. Okay. So basically, okay, I define up, and then I have some strange idea to prove these three lemmas. But maybe I am just a programmer. I just define up, and I rush on the definition of rev here. This definition of rev happens to use up. Okay. And then I am interested to show rev of rev is the same. Like for binary trees. For binary trees, I just root the function rev and could state my theorem. If I do that, you will see that actually you need more you need to show. Okay, actually, okay. If I start with this theorem here, okay, I will do that. Okay, because it is interesting, even if I don't finish everything. So let us just say intros U, and then induction. So I cannot be very fast. Induction U. Okay, well, I will be lazy because I don't want to waste my time here. But usually I should write as, okay? Induction U. So now, sorry, what happened? Okay. Okay. I start by first goal. Yes, like this. Okay. So what happens here? Rev of rev. Okay, let us just compute. Okay, this is just standard technique. I compute to see what happens, and I get, okay, something very easy, reflexivity. So you are very happy. Nothing complicated. Reflexivity. Okay. Nothing compute. Please. Yes. Yes. Now we go to the main point, which is the inductive case. Okay, rev of rev, blah, blah, blah. Okay, let us just compute. So CBN. So we simplify a little bit. And we get something. And here, the important thing to see is that you are unable to use your induction hypothesis. Oh, sorry. I need to perform my CBN. Okay. And okay, now so after computation, you see nothing similar to rev of u. You see a rev of something complicated. So here you are stuck, basically. Okay? But now you can start to think a little bit after all. You have the reverse of an up of something and something else. Okay, then it means that you need something talking about an up and a rev. At least, no, sorry. You need the rev, something about the rev of an up. Okay, this is a very important point. So you see, okay, then you could think a little bit and say, okay, when I reverse the concatenation of two lists, I should get the concatenation of those two lists, but in the opposite order. Okay, this is the first thing you should think. You need to abstract a little bit. You just forget that this is a review and this is blah, blah, blah. You just remember a list and another list. The append of two lists reversed provides something. This is exactly, so you could say, okay, now that's interesting. Maybe I should prove this one. Okay, in that case, I helped you. I already provided the interesting result. Okay, so in that case, of course, okay. But again, and you saw that in order to prove this one, you needed other theorems. And what happened basically is that here you have to look here. The very important point is that the reversed function is defined recursively with reverse, yes, but also using another function, up. This is an important point. This rev is defined with up. So it is quite natural that in order to reason about rev, you need results about up. Because rev uses up, so some algebraic properties of up will be useful. This is as simple as that. So this is big. This is the reason why we proved the result about up alone before, and also a result which combines rev with up like this. Okay, this is this basic one. Okay. Okay, this is just a little bit of mathematics that you may meet when you reason about programs. You need some result on auxiliary programs. Okay, rev is defined with an auxiliary program, which is called up. Then you need a result on up. Okay. Okay, so let us, okay, you will finish. You will write, etc., reflexivity. And then natural numbers. So what happens? Okay, I would like to, okay, so as I told you before, natural numbers are just like list, like pool list, actually, a list without elements. I just have the recursive construct, which is successor, okay? So, okay, so and then I have a O, S of S of S of O, and this is exactly the way mathematical natural numbers are constructed. And the only point I already told you is that the usual mathematical induction on numbers is just a special case of induction on this special tree, which is very poor, just a branch made of S and an O at the end. So this induction is just the one we know. So okay, again, you can prove all these theorems. They are very easy. And here you have, in particular, this one. If you define the length of a list, so, okay, we already provided the code before. You can prove this interesting theorem again, which is the length of happen is the addition of the lengths. So this can be useful for reasoning on combinations of length and up. Okay, so let us go to this point. So this is our own natural numbers, but actually these are the same as the natural numbers of the standard library. And if we print NAT, we get exactly the same definition. You can check. This is exactly the same here on the right. Okay. And an advantage is that the standard library provides a convenient notation, which is a notation we use in everyday life with 2, 6, 7, whatever. And for instance, you can prove, just check that 2 defined in this way, if written in this way, is the same as this one. But actually, you see that the goal displayed by Coq is just 2 is equal to 2, because Coq recognizes that this complicated notation here, S of O, okay, he wants to display it in the basic way. If you write set printing all, actually we would say S of O is equal to S of O. Okay, so that's the same, so reflexivity. Can I have it? Yes. Okay. So now some tricks for you, because here we proved the basic lemmas on list before. And in the same way, you have all the basic lemmas on natural numbers that you learn at the primary school or maybe later. Than plus multiplication can be defined as you may expect, and plus is exactly as the append. You plus nm, you just proceed by case and recursion on n, the first argument, like app. So all the lemmas on additions saying that 0 is neutral on the left, on the right, and is associative are the same. You have also commutativity, but for this you need an additional lemma saying that if you add n with S of m, it returns the same as S of n plus m. So this is one of the basic one, and then you get you can get commutativity. Then you have multiplication. It is defined by a fixed point again, as you may expect. You recurse on one of the arguments. So, and then you have all the basic algebraic properties as usual. So all these things are easy to prove, but reproved, so they are not for free. They are proved from the very beginning. So now in practice, you don't want to reprove them all the time. You can do that for just for you to see what happens. Locate plus the sum of 2 types. This is the sum of 2 types, which given, for instance, the type color and the type nut, you can have an element which is either a color or a nut. Usually you don't use this thing because usually the important thing is that among these 3 possible use of plus, you have the one which is interesting for us, which is this one. So you add something else if you add a type to something else or not. Coq may recognize that you are actually adding types. So this is not the same notion. This is a choice between two types, whereas this is just the usual addition of natural numbers. Okay, so the important point is that here you have this notation which is available, and then you can do print net.add. So this one, you recognize this one, and sorry, here. Okay, you want to print this one. Okay, I missed, okay. Please. Yes. So if I print it, you recognize exactly the definition you are expected to write by yourself before. Okay, so add is a fixed point which returns, which looks at the first argument n, and then if it is O or 0, you return m, and if it's a successor, you return that. Okay, exactly the same code as for list concatenation, a little bit simpler. Okay, now you can import the library nat. Okay, so in that case, instead of saying nat.add, you will see just add. I don't want to type it. I will just locate the plus now. So locate is another important, okay, like before. And what we see is a little bit, okay. The difference now is that you see that you have okay. Yes, the difference here now, you don't see net.add, you just see add. Okay, so the add, the addition that we had before. Let us try something else. We would like to see what functions, which functions, sorry, were defined with this type. So typically, we should have addition, subtraction, multiplication, maybe some other ones. Okay, we can see many ones actually. So you can see that the library is quite, okay, contains many things. So we have a notion of XOR. So you can print it to see what it is. You have a diff, law, okay, division, grid, GCD, etc. Okay, so you can see many things. And okay, so most important for us are add, mul. Okay, bitwise. Okay, okay. So the library is quite rich actually. Okay. And now, if you are interested in properties of addition, for instance, you would like to check that, for instance, associativity of addition was already proved. So you say, okay, search plus and underscore, okay, and parentheses. Okay, so you just have the syntax here, and some examples. And you can see that, okay, I have, for instance, that this theorem, actually, it is CBN should work, but we have a successor. Okay, this one also is a simplification, and we have something else. Okay, we have another sum saying that if I have a product plus n, then it is the same than n times S of m. Okay, so a kind of small distributivity. And then yet another one here. Okay. And so on. So, okay. And you can have more specific commands like this here because I had anything. I can have anything and the same here, anything than here. Okay, so I can have more accurate results. Okay, I get only this one. Okay. Okay, so it can be useful. Okay. For us, for these lectures, I will illustrate the use of coq for defining semantics of languages, and actually I don't need so much arithmetics. I will only need some very basic definition I will provide. What time is it? Okay. So maybe I will finish this file and that's all. Okay. Or maybe, okay. Maybe I will, show file. Okay, I will spend 5 minutes for the end of this file and 5 minutes for the beginning of the next file. Okay, so basically, once again, you should try to do the exercises by yourself in order to see what happens. So I define here a type for AST syntax of arithmetic expressions. So again, I have constants. I have something for the plus, something for the multiplication, something for the subtraction here. And I also added a constructor for variables. So the meaning is that if I say AVA of 3, it means the variable number 3, okay? Something that we would write x3 in everyday life. Okay, and okay, so you can try to define this kind of, sorry. Oh, I don't know how to, okay. Okay, so you know what I mean. So you can try to define this, the AST of these expressions, of these two expressions, using the previous constructors, just to see the difference between a constant like 2 and a variable number 2. Okay, two different constructors. Now, if I want to evaluate an expression, I need to say, okay, for constants, plus, etc., is like before, but now I have to say something about the variables. And it makes sense to evaluate such an expression only if I say, okay, for instance, x0 is mapped to 3, x1 is mapped to 5, and so on. Okay? So this is what we call a state. In that case, okay, so a state will just be a list of values with the implicit convention that is saying that the first element corresponds to x0, the second element of the list corresponds to x1, and so on. Okay? So I have defined my state here. You see, this is actually a list, okay? I call it state, but later I will just use the standard list of Coq. Okay, here I give this example of a state, and later I will be able to define the semantics of an expression in a given state. So, okay, you are expected to write a function. Actually, I think. Good. Yes, this is the main exercise here. So please define the fixed point just by recursive analyze of A. Okay, so you just look at A, what it is, and according to different constructors, you evaluate. And the only new thing is that when you have a variable, then you should look at the use the state, and to this effect, first you define an auxiliary function, which is here, which is get, which is supposed to be used here when I actually represents the variable number I. Okay, so if you have the variable you think you would write x2, okay, you would put a 2 here, okay. You put a state here as a second argument, and okay. Here you just have to recursively see what is I and what is S at the same time. Okay. Okay, next time I will give a solution if you are not able for, if you want to check that your solution is okay. Then there are some additional exercises saying that okay, you could shift a state and you could rename variables and check that renaming the shift provides the same thing. Okay, I think it is somewhere later. Okay, and then you can do the same for Boolean expressions. Okay, and at this stage, you already have the beginning of the while, you already have the expressions of the while language. Now, I would like to spend maybe only 2 minutes on the next, maybe you can help me, Aaron, to go to the next file. See, just to show you what will happen next time. So the 5, yes, this one. Again, something. Okay, it's okay. So just to show you what will be the language we will talk about, it is called the while language. Okay, so the while language will be made of arithmetic expressions. This one, okay, okay, exactly the same, exactly the same. Next, Boolean expressions. So if you are not able to write by yourself, you have the solution in the next file here. Okay, so the difference here is that instead of having, okay, we have two choices. We could have something similar, Boolean constant with only one constructor parameterized by a bool. Here I chose to have two constructors called B2 and B4. It's okay. Any choice is valuable. You can, doesn't make any difference. And we have, the point is that here we have two functions allowing you to compare two Boolean expressions or to compare, sorry, two arithmetic expressions. This one is the most important because this is the one which will be used basically. But you could define two of them if you want. Now we come to the main point of the while language is that it is a language which is made of instructions. The most basic one you know is assignment, okay, which takes a variable number n, okay, so we have this number here, which means the number of the variable. This is the left-hand side of the assignment, okay, variable. The right-hand side of the assignment will be an arithmetic expression, and it gets you get an instruction of the while language. Here we add also the skip, which is just the empty instruction, the no op that you have in assembly languages, for instance. Here, this is the sequential composition. So this is meant as being execute this instruction, then you get a state, and then execute another instruction. And okay, this is the sequential composition of two instructions. Here you have the if, which means that I have three components, a Boolean expression, and if this Boolean expression evaluates to true, you are expected to do the then part, otherwise the else part. Okay, so basically when you write the text, you write if blah blah blah, then blah blah blah, else blah blah blah. Okay, and you get an instruction. And the last one is the while loop, which is made, which says that okay, while this expression holds, evaluate to true, then execute the body of the loop. Okay, so two components. Okay, so this is the very basic language that which is enough for doing everything. And I added another one, which I call it imp. Okay, well, actually, okay, usually while I'm imp, but for my needs, I need the same language, which is like before, but without the while. The point is that if I have this language, which is a little bit simpler, so just skip assignment, sequence, and if, okay, I am able to define a functional semantics for it. Okay, so I use the name functional semantics. Maybe you know another name, which is denotational semantics. So it is basically the same. The denotational semantics means that you define the semantics of your language using a function. Okay. So you will see that it is possible to define. Okay, so here I have a possible solution of for get. Okay. Then okay, we can okay, here I don't, okay, here this is an exercise. Write an update function which just takes a state, a variable name I, and a value. Okay, and this you get the same state as before, except that at position I you have a new value. Okay, so this is the basic function which is used for defining the semantics of assignment. Okay, and then it is perfectly possible to define a fixed point that takes an instruction, so without while, a state, and returns the final state. So this is the initial state, the input state, if you want. You execute I, and then at the end, you get the final state after execution. Okay? So really, this is very easy. I think, okay, okay. It should take half of an hour, maybe, if you are a bit slow, to write all of this. For me, it takes longer because I am used to this keyboard, but otherwise, I think 10 minutes will be enough. Okay, so it is very easy to write that. And now, the point is that if you try the same thing about the complete language for the, not for imp language, but for the full language with the while loop, then you will get an error. And okay, so I ask you to try to do that and see why, what is wrong. Okay, there is a very important difference between this, what happens for the simple language without loop and the full language with the while loop. Okay, and then, okay, and then just to announce what will come, then we will introduce a new technique which allows us to write something which is very similar to the denotational or functional semantics of the full language, but not exactly with a function, but what we call with an inductive predicate or an inductive relation, but which follows the same shape, but with somewhat different, technically a little bit different. Okay, and one of the really important point of Coq is that we are able to reason about inductive relations in a very natural manner. Okay. So I will introduce inductive types first on simpler situation, and then we will have all the material for. So you have some time to do this. I think maybe you have 2 or 3 days to try by yourself to write these functions. Okay, to see what happens. So try by yourself. I will give some solution or partial solution to you in maybe two days, something like this. Meantime, we will study what are inductive relations. Okay? So thank you for your attention. And sorry for the technical
That's okay. Thank- Thanks for this lecture. 会议结束一下。有问题吗？从网上有问题吗？能？你们线上连吗？那
I from that group.